Hello everyone, we are starting our first chapter, Basic Concepts. In this chapter, we are going to be covering a lot of terminology, a lot of the basic concepts that we're going to be covering in the course. Most of what we're covering is something that we'll be using for the remainder of the course. And sometimes, if you've looked over the syllabus or watched the introductory video, you'll know there's activities that go along with some of these lectures, and this chapter does have an activity with it. So if you look in the weeks folder, you will see an activity, and I recommend if you want to go through that, you might want to do it with as you're going through the video lecture. It might make it a little bit easier as we're going through the concepts. Activity keys are always posted after we've covered a topic, so you can always check your answers there. So the goals for this chapter are to understand the differences between descriptives and inferential statistics. And so with those two different types of statistics, essentially what we're going to be doing, descriptive statistics is kind of just describing the data we have, and then the inferential statistics will be using that data to make inferences about the population. So for the first unit or so, even most of the second unit, we'll be talking about descriptives, and our goal is to kind of move into inferential statistics to be able to analyze the data that we have and make some conclusions and generalize that to the population. We will also be talking about a subject or individual variables and different types of variables in general, and we'll also want to go through some of the basic concepts underlying statistics, like what is the difference between a correlation and an experiment? What is the difference between an independent and dependent variable, which we'll often refer to as IVs and DVs? And as I mentioned, inferential and descriptive statistics, being able to define them and know when we're using which and why. We'll be identifying variables as either qualitative, which is also known as categorical, or quantitative, which are also known as continuous variables. And you'll want to be able to use those terms interchangeably, because sometimes in the textbook it'll talk about qualitative variables, and sometimes it'll talk about categorical, and knowing that those two are basically talking about the same thing will be helpful, especially as you're working across, assignments, activities, homeworks, exams, those types of things. So know that when it says qualitative, it also means categorical. When it says quantitative, it also means continuous. They're just different terms for the same thing. We'll be identifying the scale of measurement. SOM is the acronym, the abbreviation that you will sometimes see. And essentially when you see this scale of measurement on an assignment, on an activity, on a homework, it's asking you for the scale of measurement. So being able to identify what we're talking about and getting familiar with how we communicate with these different terms. But we'll be identifying different scales of measurement for the variables that we have based on the data, the way we have our data recorded. We can record our data in any number of different ways. How we record it is going to require a different scale of measurement. So knowing why scale of measurements for a variable is important will become clear when we start talking about what type of tests are we going to run. It's going to depend on the scale of measurement that we have. We can only use certain tests for certain scales of measurement. So we're going to start off being able to identify variables with the scale of measurement so that we know what we're working with. So what are statistics? Basically, they're a way to organize and summarize the data that we've collected, but just as important, we want to be able to present this information to other people as well. So we're going to be determining what conclusions are justified based on the results that we obtained. Essentially what we're asking is, what's the most likely explanation of what happened with our data? Can we say that a treatment is working or that it's not working? Can we say that one treatment is better than another? So what conclusions essentially are justified based on what our data is telling us? So it's a mathematical way to organize, summarize, and interpret information, but also a way to present this information. So some different vocabulary that we're going to be starting off with is the population. We'll often be referring to, what is our population of interest? And when we say that, it's talking about all the individuals of interest in a study. So it's not talking about the people that we have in our study necessarily, but who do we want to generalize our results to? So it could be college students in the United States, but maybe it's only college freshmen only. Maybe it's college freshmen only at WIU. Maybe it's college freshmen on the East Coast, right? So what is our population? And that is referring to anybody that we want to generalize our results to. Our sample is the set of individuals selected from our population, and it's intended to represent the population, so that if we get whatever size sample we get, and we'll talk about how large our sample needs to be in order to make inferences, but in essence, it needs to represent the population, because again, whatever statistics we're doing, whether it's descriptive, whether it's inferential, we want to be able to get a representation of what the population is that we're actually wanting to talk about and make references towards. So we only use samples because usually we can't get the whole population. If we could get the whole population, we would need statistics. Right? We would have everyone in the entire group that we're wanting to make inferences about. So a sample wouldn't be required. But because we can't do that, we collect a sample, a smaller subset of the population that we are using to represent that population. Continuing on vocabulary, our data, our datum, whether we're talking about singular or plural, is essentially our measurements or the observations that we've taken. We usually collect this in some kind of statistical software. Now, we won't be working with statistical software in this course. Generally, people will use things like SPSS. If you've had a statistics course before, you might be familiar with that, but we are not going to be using the software. But generally, we record our data in some sort of software, and then we look at the measurements, we look at our observations, we see what's going on, and then we talk about our study. So parameters versus statistics. Parameters are our values, again, referring to the population, right? So parameters are talking about the population, statistics are talking about the sample. So, for example, we might have an average for our population. And I say average in this example because generally that's what we're going to be working with. We're going to be working with the mean or the average from our sample, and we're going to be trying to make inferences about what the mean or the average is in the population. So if we wanted to get the mean or the average for the entire population, we would have to take a measurement from every single individual in the population. Like I said, that's not really feasible in most circumstances, so we're going to get a statistical value, an average from our sample, and that's derived from taking a measurement of every individual in the sample. And then we'll use those statistics, again, generally the mean or the average of our sample, to make inferences about parameters, which is the average in this example for the population. With descriptive statistics and inferential statistics, primarily with descriptive statistics, what we're trying to do is summarize our data, simplify it in some way. We're really just describing the sample that we have. We might get the mean for some of our variables, but we're describing again the sample, whereas with inferential stats, what we're doing is we're using our sample as well, but here we're using it to make inferences about the population. So if we get a mean, we can't really, a mean of our sample, we can't use that to say, okay, that's what the mean in the population is too. We have to do some other things, and that's what we'll talk about when we get to the different inferential statistics that we're going to be using in the course. So descriptive statistics, they're describing a sample. Inferential statistics, they're using a sample to make an inference or generalization about the population. One of the really important terms to be familiar with, because it's going to come up throughout the entire semester, is sampling error. And sampling error is the amount of error that we expect between our sample and the population which is expected just based on chance alone. It's not error in a sense that we did something wrong, there's a mistake that's been made. It's a naturally occurring discrepancy between what we find in our sample and what actually exists in the population. We could also look at it from sample to sample, and I'll use IQ for an example. I use that a lot because we know a lot about that variable and what it looks like in the population. For example, we know that IQ is 100 in the population. But if we were to take a sample and measure IQ and get a mean average from our sample, we might get an average of 98. And then if we take another sample, we might get an average of 104. And if we take another one, we might get an average of 106. Right? The point is that from each sample that we take, we don't expect it to be exactly the same as the next sample. Right? There's going to be a little bit of difference between each of those samples, and likewise, there's going to be a little bit of difference between our sample and the population. Now, we expect it to be roughly similar, somewhere in the ballpark, unless we're working with a very unusual sample. We expect it to be somewhat similar to the population, but even then, we're working on a distribution, and that's something we'll talk about later, sort of around chapter 7, when we start talking about multiple samples and when we get averages from those multiple samples. But for sampling error for now, it means the same thing regardless of what chapter we're in. It's just going to be applied differently depending on what concepts we're working with. But it's always meaning the same thing. It's the amount of error that we expect between our sample and the population just based on chance alone. And later, we'll actually have a formula, a mathematical formula that allows us to calculate sampling error so that we can subtract it from our study, from what we're looking at. Like, let's say we have a treatment group and a non-treatment group, and we want to know if there's a difference. Right? We're going to be looking at the means of the treatment group and the means of the non-treatment group, and we want to know if those two means are really different. How can we tell that they're significantly different? Well, the first thing we need to do is remove any sampling error, because the differences we're seeing might be due to that and not due to our treatment that we provided. So it's going to become important so that we can quantify it and then acknowledge it in our data analyses as well. So correlations and experiments, you've probably heard a little bit about these different methods, even if you haven't had a statistics class before. And you've probably heard the term correlation does not imply causation. If you've had an intro psych course, you've probably heard that, and they've probably talked about why that is. When you're running a correlation, you're only observing two different variables to determine if there's a relationship, if the two things are related. It never implies, if you do see a relationship, that one variable is causing the other. And the most common example used to demonstrate this is ice cream sales and crime rates. We know that as ice cream sales go up, crime rates go up. We see this relationship again and again. It doesn't mean that eating ice cream is causing people to commit crimes, right? Something else is going on. In this case, it's weather, right? As it gets warmer, ice cream sales go up. As it gets warmer, crime rates go up. So both of these things are affected by the weather. Both of them are increasing because the temperatures are increasing. It doesn't mean that, again, ice cream is causing crime. So how do we tell when one thing is causing another thing? The only way to tell is through an experiment. And with an experiment, you're systematically manipulating variables to determine whether changes in the variables that you're manipulating are causing the changes in the variable that you're measuring. Let's say, for example, you want to determine whether medication or treatment or therapy, for example, so medication or therapy is having a better effect on anxiety levels. So what you're manipulating is whether a group gets medication or whether they get therapy. And what you're measuring to determine which of these is better is anxiety level, right? That's the variable that's being measured. So again, the only way to determine cause and effect relationships are to run an experiment. However, there has to be control in place to ensure that other variables aren't actually responsible. Any other variable that's causing differences between your treatment groups is a confound, right? And sometimes we can anticipate what a confound might be, and sometimes we don't, and we're not aware that it's actually a confound causing the difference between the groups. So what might a confound be in our example if we're using medication and therapy to determine which is better for anxiety? Well, we might have a confound like the time of day, right? So if group A is getting medication, and we always measure their anxiety level in the morning, and group B is getting therapy, and we always measure their anxiety levels in the evening, then it might be that any differences that we see between those two groups in anxiety has nothing to do with whether they're taking medication or getting therapy, but everything to do with the time of day we're measuring it. For example, it could be that anxiety levels are higher in the evening, and so it's going to make it look like the therapy group who's being tested, or who's, we're measuring their anxiety levels in the evening, that their anxiety is higher, and maybe it makes it look like the therapy isn't as effective as the medication, when that's not the case at all. So we always want to be really careful of any possible confounds. And again, some of them we can anticipate, right? We want to keep everything as consistent as possible. When are we measuring anxiety? How long are we taking measurements, right? You want that to be the same between the two groups in order to ensure that you're not getting differences that are due to confounds and not your actual independent variables that you're interested in. So what types of variables can we have, right? First off, we want to define a variable, and it's a characteristic or condition that has different values for different individuals. It can be level of anxiety, it can be weight, it can be height, it can be IQ. There are many different types of variables that we might be interested in. Participant variables are individual characteristics like height and IQ that we can't change. We can't really do anything about those variables. They are what they are. They're inherent to the participant. We can't change someone's height. That would be an individual characteristic, or what we call a participant variable. Environmental variables, on the other hand, are differences like weather or room size, things that are inherent to the environment themselves. Sometimes we can change them, sometimes we can't. But it's important to know, because if we are interested in something like gender, and we're saying, okay, we're looking at males versus females, those are individual characteristics that we can't change for the purposes of our study. And that will become important when we talk about the types of independent variables that we can have. Right, so independent variables, or IVs, which we'll often refer to throughout the course, are the variables that are under the control of the researcher. If you're running a true experiment, they're manipulated before you measure the dependent variable, or the DV. The dependent variable, or the DV, on the other hand, is the variable that you're observing and you're measuring to determine what the effect of the IV was. So if we're going back to our example to look at medication versus therapy and how that affects anxiety levels, our dependent variable here would be the anxiety level. That's what we're measuring. And the independent variables that we're manipulating before we measure are whether participants are getting medication or whether they're getting therapy, right? And so it has to be done before. It wouldn't make any sense to measure anxiety and then provide treatment, whether it be medication or anxiety, because you wouldn't be able to determine what effect your independent variable has had. So again, whatever you're manipulating, it's done before you measure that variable. Sometimes it could be done on at multiple points, and you take multiple measurements of anxiety, for example, to see if there's a time difference. But in general, just for simplistic purposes, IVs are what we're manipulating. We do it before we measure the DV, which is our dependent variable. So circling back around to confounds, right? One of the confounds that can be really problematic is a lack of random assignment. So when we say random assignment, what we're doing is randomly assigning participants to groups to make sure that there's even placement of participant variables. So if you remember back, we were just talking about participant variables. These are things that we can't change. It could be gender, it could be IQ. I mean, there are a number of things that people differ on individually. But if you use random assignment, it's much less likely to occur the case where the differences between your groups are due to participant variables. For example, if you put all of your males in your medication group and all of your females in your therapy group, then that would be a confound, because we don't know if it's medication and therapy that's causing differences in anxiety levels or if it's inherent differences based on gender, right? But if you randomly assign your participants, then you can ensure that there's even placement, again, across those variables, so you don't have to worry so much about individual differences causing the differences in your experiment. Sometimes we have the case where we match groups to be equivalent, and this might happen if you are looking at running a study that was done a very long time ago, right? It's done in the 1970s, let's say, and you want to take a group from today's time and match it to that cohort group. You would want to make sure that you're matching on the variables that are of interest. So if this study in the 1970s used individuals with an IQ greater than 120, then you want to make sure your groups match that cohort as well. So you want to look at individuals from today whose IQ is over 120. And maybe you're matching across different types of conditions, right? So if in the 1970s they had a group of participants that had an IQ between 80 and 100, and another group that had an IQ between 100 and 120, then you want to match your groups to be equivalent across those conditions. And you also want to hold constant any other variable, right? Keep everything the same whenever you can, right? So you can imagine, right, if you want to look at a teaching method to see which one is more effective. And the way you're going to measure this is how well people perform on a final exam. Let's say that. Then you want to make sure that across all of your groups, whichever teaching methods you're using, we'll say teaching method A, teaching method B, teaching method C, that you are doing everything the same across those three groups. So you wouldn't want to hold a final exam for group A at 8 o'clock in the morning and group B at 12 o'clock in the afternoon and in group C at 8 o'clock at night, right? Everyone should be basically taking it at the same time. You also want to make sure that the environmental conditions are the same. So they're taking the exam, either everyone's taking it in a different room than when they learn the material, or everyone's taking it in the same room when they learn the material, right? So you wouldn't want to take group A and say, okay, we're going to move you to a different room outside of the classroom that we learned this material in, you're going to take the exam, but for group B and C, we're going to take it in the same room, right? Because there could be something just as minor as a room difference that's causing an overall difference in the exam scores that we're seeing. And it may not be due to our teaching method. So again, with confounds, the best way to minimize them is to keep everything the same whenever possible. It's also, like I've mentioned before, it's possible that you could have a confound and you're not even aware of it, right? In the activity sheet, it asks, what are some possible confounds, right? It could be anything. It could be that, for example, in our teaching method group, that for some of our participants, there was something going on when we did the final exam testing that was different from the other groups and we weren't aware of it. Maybe there was a fire drill, maybe the air conditioning conked out and it was really hot for that group, but it wasn't for the other groups, right? And we weren't really aware that that was happening. So when we are aware, we want to be able to anticipate it, hold it constant, but also be aware that there could be things going on that you're not really focused on, or that you may not even be aware of yourself as the researcher. So we have experimental conditions. In an experiment, we also have control conditions. The experimental condition are the group that's receiving the treatment or the stimuli, whatever it is. And the control condition is the group that's receiving no treatment, no stimuli. You've probably heard of placebo effects, right? Placebo groups are your control conditions generally, so those that aren't getting the treatment that you're providing in your study, that you're trying to see if it makes a difference. Why do we need a control condition? Well, in medication trials, for example, we know that there is this placebo effect, that people think that they feel better just because they think they've received a treatment, and it may not have anything to do with the actual treatment itself. So what we have in those types of studies is an experimental condition, and oftentimes the participant themselves and the researcher themselves, that's called a double blind, doesn't know who's getting what, if they're getting the actual treatment or if they're getting the placebo. And that way, if everyone's doing the same thing, we're controlling for that confound, for that placebo effect, right? If people in the controlled condition start saying they feel better, then we have a baseline to measure, like, if people that are getting the actual medication, the treatment medication, if they're doing better than those in the placebo group or the control condition, then we know that it's the medication that's causing it and not the mindset of the participants who are just feeling better or reporting fewer symptoms because they've received, or they think they've received, a treatment. So there are non-experimental designs too, and those are the ones that we often refer to as quasi experiments, and that is the case when we use quasi-independent variables. So I've mentioned that there are participant variables, and those could be things like age or gender or IQ, but we can't randomly assign them, right? We can't make someone a certain age, and because of that, because we have no control over it, we can't randomly assign them to be in a male group or a female group, or an 8-year-old group or a 10-year-old group. In that case, random assignment is not possible. And so non-experimental designs we call quasi experiments, and it could be where we're doing pre and post testing. People that have gotten a test prior to a treatment, and then they have a treatment, and then they do a post testing. We can't randomly assign them. We need the people in the pre-test group to be the same people in the post-test group. In that case, there's no random assignment, so it's a quasi-experiment. It could also, again, be age-driven. If we want to see whether 5-year-olds versus 10-year-olds versus 15-year-olds remember certain types of material better, we can't randomly assign 15-year-olds to be in the 5-year-old group. It doesn't make any sense. It's age-driven, and therefore it's non-experimental in the sense that it's quasi-experimental, right? We can't use random assignment for those types of studies where our actual independent variable is driven by a participant variable, or it consists of a participant variable. So what are some different terms, right, that you want to be familiar with experiments? One is, we talk a lot about constructs. These are attributes or characteristics that you can't directly observe or measure. That would be things like hunger or anger or IQ, right? These things are subjective. What do we mean when we say someone is hungry? Or if we say a certain length of time has passed after an incident, people are going to be less angry. What do we mean? How do we define angry? What are we using to measure anger? And there are a number of ways we can do that. We can ask people, how angry are you? We can observe them and see if they have angry expressions. We can determine whether or not they decide to help other people in certain circumstances, and see if higher anger is related to that. Another example listed here is hunger. Like, how do we measure hunger? We can ask people, how hungry are you? We can put it on a sliding scale from 1 to 10. We can basically look to see, some studies have done this where they've actually had people swallow a balloon and see if, how often their stomach contracts, and the balloon measures basically stomach contractions where people's stomach growls, and they say, okay, more contractions is related to more hunger, and that's the way we're going to measure hunger, right? So there's all kinds of different ways. We can use many different ways to define a construct. The point is are we being really clear about it? And that's where operational definitions comes in. So it allows constructs to be measured by defining it in terms of how you're measuring it. So we can say high IQ, like we want to test whether individuals with a high IQ perform better on certain tasks. Well, we need to define what we mean by high IQ. So an operational definition of that might be a score on the Stanford Binet that's greater than 130. That's what we mean in this study when we say high IQ. Right, we have discrete variables, and we also have continuous variables. Discrete variables, or as I mentioned before, they're also oftentimes called categorical variables, are separate individual categories, meaning they're mutually exclusive. What that means is that you can't be in two categories at the same time. You can be, if you're looking at age, for example, you can be in the 8-year-old category, or you can be in a 10-year-old category, but you can't be in both at the same time. Another example is number of children people have. You can have 2 kids, or you can have 3 kids, or you can have 4 kids, but you can't have 2.5 kids, and you can't have 2 kids and 3 kids at the same time. So when we're talking about categorical variables, it's one category that you can belong to at any given time. Continuous variables, on the other hand, you have an indefinite number of values that can fall between any two observable values. This could be height, it could be weight, it could be test scores, right? So you can be 6'2" and 3/4, right, for height. You can be 130.2 pounds, right? So you can fall in between. You don't just necessarily go into one category. Test scores are another example. We can measure test scores any number of ways: high, low, medium, or we can say raw scores, right? 72 versus 85. These are more continuous, right? There's an indefinite number of possible values that can fall between any two of those. What's high versus what's low. It's a continuous measurement. So this brings us to our scale of measurement, and depending on our scale of measurement, there are a number of different statistical procedures that are available. And so our first up, there's 4 that we're going to talk about, and the first one is nominal. And this is categorical data. It's based on names. It has no qualitative value. It could be things like color or college major or occupation. And you can't really determine a numerical difference between those categories, though you might assign numerical values arbitrarily to different groups, right? You say, we do this all the time: treatment group, group 1, treatment group, group 2, treatment group, group 3, right? But those 1, 2, and 3 numbers that we're assigning don't have any numerical value. We might assign colors, right? Blue group, yellow group, red group, and we assign blue a 1, yellow a 2, red a 3, so that we can take and basically organize our data. But those numbers don't inherently mean anything, right? So there's no mean or average that you can collect from assigning nominal data. It wouldn't make sense to do that. Right, some other examples of nominal data would be, what city are you from? Chicago, Cleveland, Davenport. All of these might be associated with a number. Chicago is 1, Cleveland is 2, Davenport's 3. But the number doesn't mean anything. It's arbitrarily assigned. We could also say Davenport is 1, Chicago is 2, Cleveland is 3. Right, so it's arbitrary assignment. What kind of car do you drive? A Ford, a Chevy, a Saturn, a Honda, so on and so forth. What religion do you identify with? What political party do you identify with? What type of vitamin did you give to your patients? Sex is a common example too, male or female. These numbers that we assign to these groups don't have any meaning, right? Sometimes we may not assign in a number, but with nominal data, it doesn't have any numerical meaning inherently. Second up is our ordinal scale, rank observation in terms of the size of the difference, right? So we can determine with ordinal scale data that there's a difference, and we know what direction the difference is going, but we don't know how much difference exists. So example of this would be placement in a race, first, second, or third. We know that first is more than second, second's more than third, but if someone, let's say, wins a timed race, we don't know how much faster they were, the first place winner was, than the second place winner, and then the third place winner. We don't know how much difference exists between them. Same thing with small, medium, and large. If you get a large, how much bigger is that than a medium, right? So if you go to a restaurant, you'll see oftentimes they put up little examples, like a soup cup or a drink cup, to show you, like, this is a small, this is a medium, this is a large, because just telling you, all you know is one's bigger than the other. You don't know by how much. So that's another example of ordinal data, freshman, sophomore, junior, senior, another example. We know that seniors have been at school longer than freshmen. We know they may have more credits, but we don't know how much more. We don't know how much more time they've spent or how many more credits that they have. And so another example of ordinal where we know one is more than the other, but we don't know how much more. Other examples include income level. When we're measuring income in terms of categories, and we often get surveys like this where we're asked to determine essentially how much do you make or how old are you, and they'll give us these categories. Are you making between 0 and 20,000, 21 and 30,000, 31 and 50, and so on. So if you were to see two people, one falling in the 31 to 50 category and another falling in the 21 to 30 category, you don't know how much the first person makes, how much more they make than the second person. All you know is they make more, right? And that's all you can really determine with ordinal data. Rank in the military is another example. E1, E2, E3, and so on all the way up to O10. We know that one rank is higher than another, but we don't know really what that means. Like, how much more rank are we seeing? How often do you park on campus? Never, sometimes, most of the time, always. If someone selects always, we don't know how much more they're parking on campus than someone that says most of the time. And we often see this again with these Likert type scales. Again, they call them Likert. When you get a scale and you're asked to pick, like, how often do you do this, or how much do you like this, or how upset does this make you, on a scale of 1 to 5, or 1 to 10, or 1 to 100. The example here, how much do you agree with the statement that the governor of Ohio should resign? Totally disagree, all the way up to totally agree. We only know that one is more than the other. We don't know how much more. If you say you really like someone does something and you rate it a 10 on a scale versus someone else that says an 8, how much more, right? Again, we don't know. We assume that the person who selected 10 likes it more than the person who selected 8, but we don't know how much more. So our third scale of measurement that we're going to talk about is interval scale. And with interval scale, the differences between the values have actual numeric meaning, and the numbers are equal in size. as we go across the scale. So temperature is an example. Here we have 1 degree increase if you go from 70 to 71 degrees versus 85 to 86 degrees. That's still a 1 degree increase. It's the same amount. IQ measures are another example of this. But the key with interval scales is that 0 is arbitrary. It doesn't mean that there's a total lack of the variable that we're interested in. So if you say it's 0 degrees outside, doesn't mean that there's no temperature outside. If you say someone has scored a 0 on an intelligence scale, it doesn't mean that they have no intelligence at all. Some other examples of interval data would be degrees in Fahrenheit. Right, so we talked about temperature already, but again, while the intervals are consistent as we move up and down on the scale, it doesn't mean that if you have a 0, it's a complete lack of temperature. If you're talking about years, right, 1960 versus 1985 versus 2000, or 0, it doesn't mean that 0 means there's no time at all, right? Not in the case of years. Now we can look at time in different ways, like seconds or minutes or things like that, where 0 actually does mean a lack of time. But if we're talking about years, obviously we can go start from the year 0 and know that there was time before that year as well. With ratio, there's a similarity with interval data in that the differences have equal size and they do have numeric meaning, but with ratio data, 0 is no longer arbitrary. This would be things like weight and height and time. These things can't be negative. You can't be negative 100 pounds, right? Once you get to 0, that's it. There's no weight. 0 means actually a lack of that characteristic, no weight whatsoever. Height, 0, no height whatsoever, right? Seconds, 0 seconds, no time whatsoever. So 0 is not arbitrary with ratio data, but it also allows for ratio comparisons. And that's not true with interval data. So if you have 10 seconds, for example, you know that's twice as long as 5 seconds. That's not true with interval data. If you have an IQ of 140, for example, it doesn't mean you're twice as smart as somebody with an IQ of 70. Other examples of ratio data: how many siblings do you have? If you have 0 siblings, you have no siblings. There are actually none, right? 0 is not arbitrary, it means none. You can also have ratio comparisons. Someone that has 4 siblings has twice as many as someone that has 2 siblings. Right, so if you can make those kind of ratio comparisons and 0 means 0, you know you're working with ratio and not interval data. Same thing with how much money do you have in your wallet. You have $0, that means no money, right? Nothing. But somebody with $20 has twice as much as someone with $10, right? Same thing with how much do you weigh. Somebody that weighs 240 pounds is twice as heavy as someone that weighs 120 pounds. And if there's 0 weight, that means there's no weight at all whatsoever. So again, an example of ratio data. Typically, when we are working with nominal ordinal data, we have discrete variables, and we can also have ratio interval data, and that's going to be working with continuous variables. So typically, but not always, nominal or ordinal data is a discrete variable, whereas ratio and interval data is a continuous variable. So once we've decided that we are in fact working with categorical data, that is the data is falling into a mutually exclusive category, we then want to decide whether it's nominal or ordinal. So the question we want to ask here is whether or not there's some sort of ordering of the categories that everyone agrees on. Again, that might be something like first place, second place, third place. Everyone agrees that first place is higher than second place is higher than third place. If we don't have any kind of ordering like that, then we're working with nominal data. So that could be something like colors, right? If we decide we're going to have a yellow group, a blue group, a green group, And even if we assign numbers to those groups, those numbers won't mean anything. And no one really agrees on what the numbers mean. So in that case, we're working with nominal. But if we do have some hierarchical structure, even though we can't tell how much difference exists between the categories, there's some structuring that everyone kind of recognizes, small, medium, large, and so on, then we're working with ordinal data. Otherwise, if you're working with continuous variable, then it can be either interval or ratio. And the question you want to ask here, there's a couple of them you can ask. One is, does 0 mean a lack of a characteristic? Does 0 actually mean nothing? If it does, then you're working with ratio data. If it doesn't, then you're working with interval data. You can also ask, does one value equate to twice as much as another? If yes, again, you're working with ratio data. If no, then you're working with interval data. So for any given variable, we can record the information in so many different ways. So because of that, we can have different scales of measurement for any given variable, even though we're measuring the same characteristic. As we were talking about early on, if we're trying to determine how hungry someone is, we can ask them on a scale of 1 to 10. We can check their blood sugar. Maybe that would be an indication. We can have them swallow a balloon and see how many times their stomach growls, right? If we ask them on a scale of 1 to 10, that's a different scale of measurement than if we're trying to measure how many times someone's stomach contracts, right? Because it can contract none, which would be 0, absolute 0, or it can contract 10 times, which would be twice as much as someone who's contracted 5 times. So that would be a ratio variable. But if we ask them on a scale of 1 to 10, right, we can't tell how much difference exists for someone that says 10, I'm very hungry, versus 8, I'm pretty hungry. We don't know how much hungrier the person who selected 10 is than the person who selected 8. So that would be ordinal. And oftentimes, Likert type scale data is ordinal, although we'll talk later in the semester, it's also used as interval in a lot of research studies for a number of different reasons. But technically, it's ordinal data. So let's look at this example of age. How old are you? And we can ask that in any number of different ways. We could say, how old are you in years? 34 years old. We could say, how old are you? Check one of these categories, 0 to 19, 20 to 39, 40 to 59, and so on. Or we could just say, how old are you the correct age, or are you not the correct age? So if we're asking how old you are in years, that's going to elicit a very different response than how old are you based on one of these categories. So how old are you in years? We're looking at this question, the way it's asked, the data that we're going to get is essentially ratio data, right? Because 0 means 0 years old. Someone who's 20 is twice as old as someone who's 10, right? So we're working with continuous data here, and it would in fact be ratio. If we're asking how old someone is by category, and someone selects the 20 to 39 age range, we know that they are younger than someone who selects the 40 to 59 group, but we don't know how much younger, right? So we don't know in that case if we would be working with ordinal data, because we know there's a difference, that they're younger than the 40 to 59-year-old who selected that category, but we don't know how much. So if we ask, how old are you, correct age, not the correct age, we're working with nominal data. We might assign 0 to the correct age and 1 to the not correct age, but the 0 and 1 doesn't mean anything, and we can just as easily flip those around. So in that case, we're working again with nominal. So take a minute and look at these questions here and determine, you can pause the video, determine whether or not you're working with categorical or quantitative data, and then what scale of measurement you're working with. So again, pause the video, have a look at each of those, see what you come up with. So first off, are you classified as a senior? Yes or no? We can assign a number to yes and no here, 1 and a 2, but the first thing we notice is that it's categorical data. You can be a senior or not a senior, but you can't be both at the same time. You can't be a senior and not a senior at the same time. So we're working with categorical data, but the numbers, if we did assign any, wouldn't mean anything. So here, we're working with nominal data. The next question, number of credits you're taking this semester. We do know that we're working with we're working with quantitative data, right? Because the intervals are increasing consistently between 1 and 2 and 3 and 4 and so on. So consistent intervals. But we also know that you can be working with 0 in an arbitrary sense. So 0 actually means no credits whatsoever. We also know that we can do ratio comparisons. So someone who's taking 16 credits is taking twice as many as someone who's taking 8 credits. So in this case, we're working with ratio data. Next one, sex, male or female. Again, mutually exclusive categories. You can only be, in this sense, in one of the categories at any one given time. And the numbers that we assign don't necessarily mean anything. We can assign female 0 or 1, male 0 or 1. So for this, again, nominal data. Zip code. It looks like there's not a lot of numbers here. Maybe we're working with something more than categorical data, but in actuality we're not. We know that these are mutually exclusive. You can only be in one zip code at any given time. So you can be in 43606 area, or you can be in 49505 area, but you can't be in both at the same time. So we're working with categorical data. In essence, the numbers here don't have any numerical meaning in the sense that one is greater than another, right? So the numbers that we're using have meaning in that they identify with a certain location, but they don't identify with a quantity of being more than or less than. So in this case, again, we're working with nominal data. Income level, we kind of went through these categories before. We know that if we pick, let's say, 41 to 60, and someone else picks 21 to 40, we don't know how much more the person in the 41 to 60 category makes than the person in the 21 to 40 category. We know they make more, so then the categories have numerical meaning. One's greater than the other, but we don't know how much. So in that case, we're working with ordinal data. Father's type of job, blue collar, white collar. Here, again, we can assign numbers, 1 for blue collar, 2 for white collar, but those numbers wouldn't necessarily mean anything. No one knows but us what they mean. You can only be in one category at a time, so categorical data, just like income level, just like zip code, just like sex, and also just like senior. So we're working with categorical data. The numbers don't mean anything. Again, nominal data. For IQ, here we've talked about this a little bit before. The numbers have meaning, right? Having an IQ of 100 is more than someone who has an IQ of 80, but how much more, right? We can't do a ratio comparison here. In addition, having a 0 IQ doesn't mean having no intelligence. So in this case, we're actually working with interval data. So take a look at scale of measurement. You'll see it on the homework assignment, and you'll see it on exams and in the textbook, and you want to be really familiar with scale of measurement because it's going to be important in determining later on down the line what we can actually do with the data we have. What tests can we run with it? What can we say about it? What descriptives can we use with that type of data? So that's why we're kind of starting off here with scale of measurement, because it kind of determines everything that we do moving forward. Right, so what I just said is kind of explained here as well. For each scale of measurement, only certain statistical analyses are going to be appropriate. And we'll talk more and more about that throughout this semester. But when we look at something like, for example, religion, We could have people that are atheist, Buddhist, Catholic, Methodist, all the way through whatever we can think of. And we can assign all of those numbers, but those numbers won't inherently mean anything. Even if we see, values assigned to them, we can't say, okay, we're going to take the average and we'll say Methodist is the average person. It wouldn't make any sense to do that because this is nominal data, right? We can get quantities of how many people fall in each of these categories and then try to determine something from that, but the categories themselves don't tell us anything numerical. If we assign atheist 1, Buddhist 2, Catholic 3, Methodist 4, and so on and so forth, we can't add those numbers up and divide and get an average. It doesn't make any sense. So based on the scale of measurement we have, that's going to determine what we're going to be able to do. So I always try to include a slide like this at the end of each lecture, so we have a summary of any of the new notation that we have come across or that we've started to use, and we'll just keep building on that. And I do that because I think one of the hardest things for students, and for myself when I was a student, was learning the statistical language, because it is in fact a different language, right? Some of these symbols you may not have seen before, you don't know what they mean, you don't know what they're called. So as we come across new notation, new symbols, I'll include them so that we know what they're called, what to expect when you see them. For example, when you see uppercase sigma, and I say uppercase because later on we'll start talking about lowercase sigma, and that means something different, it looks different. But when you see uppercase sigma, it means add everything up after that sign, after that symbol. So sum everything together. When you see uppercase N, in statistics, that's generally referring to the population size. I say generally because as we start working with more complex designs, N could be used for sample sizes as well if we have multiple samples that we're talking about. Lowercase m, N generally refers to the sample size that we're working with, or if we have multiple samples, each of those groups and what their sample size is. So sigma was primarily used, that's something generally you'll see across all mathematics, not something that you'll see change a whole lot. But statistical notation can change from textbook to textbook. And this is another reason I want to keep all of our stuff in one place and kind of reviewing it so that you don't get confused. Sometimes they'll even use two different symbols for the same thing. And if that happens, I'll be putting that on this page at the end of each lecture so you know it's talking about the same thing. And then there's also a difference between things like sigma that you see across all mathematics, and then things like n, which you see primarily meaning something different in statistics than you do in other areas of mathematics. So in any case, I'll be keeping a slide saved for our notation, again, because it can be pretty frustrating to try to learn the notation along with the new concepts that we're covering. Last thing, our textbook has a section for reviewing basic mathematical operations, things like PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction, those kind of things that you might remember but that might not be so fresh in mind. So you may want to take some time to review the textbook for some of those basic operations. So that's a wrap for chapter 1. We'll get started on chapter 2 this week as well. And that concludes this chapter.